So the first thing we're going to do in this question is write down some probability axioms and properties. These are just useful facts and like shortcuts we have, or formulas we have when we're working with probabilities that can come in handy when solving problems like this one. So let's first write out some probability properties or axioms. So we'll start out with some pretty simple ones. So basic facts. One is that the probability of any event is always between 0 and 1, right? 0 being the lower bound, meaning it doesn't happen ever. 1 being this event is always happens, or it's always true. So probability should be a number between 0 and 1. The probability of the complement of any event, so the probability of not A, is always 1 minus the probability of that event happening. So the probability of not A is always 1 minus the probability of A. We can also rearrange this to get a useful property, which is that the probability of any event plus its complement is always 1. Okay, another useful property we have is called De Morgan's law, named after the guy who discovered it. And that says that the probability of the complement of the intersection, so the probability of not A and B, is equal to the probability of the union of not A or B. So in other words, I can convert the complement of an intersection to a union in this way. Another fact we have that's useful is that the probability of the union of any two events is equal to the probability of one of those events plus the probability of another minus the probability of their intersection. For explaining why that's true, it might help to use a Venn diagram, just to give you an intuitive sense of why, how we come by this property. So let's call this event A, and I'll call another event B, and let's assume that, they have an intersection, that they overlap. They're not disjoint. So A or B, that's everything in A plus everything in B, right? That's A or B. So, in other words, this is the union, everything I've shaded in. So it's A plus B, but notice that I shaded in this area in the middle twice because I counted it as part of A and I counted it as part of B. So in other words, I've double counted the intersection, this overlap area. So that's why we consider the union of two events, or the probability of the union of two events, to be the probability of the first plus the probability of the second minus this area in the middle once, so to avoid double counting it. Okay, and then remember that if A and B are disjoint or mutually exclusive, by definition, that means that their intersection is empty. So the probability of their intersection is 0. So if A and B are disjoint, this same property becomes just the sum of the probability of A plus probability of B minus the probability of the intersection, which if they're disjoint is 0. Okay, so these are some useful properties to have in our back pocket. Put these over here. So let's do some problem solving. So let's say we have an event A, and the probability of A is 0.3. And we have another event B, which the probability of it is 0.4. And the probability of their union is 0.6. First, let's find the probability of not A. Well, by definition, this is the probability of the complement of A. And, well, we know what the probability of A is. It's 0.3. And we know one of our axioms or properties is that the probability of the complement of any event is just 1 minus the probability of that event. So the probability of not A is 1 minus the probability of A, which we know is 0.3. So the probability of not A is 0.7. Okay, now let's suppose we want to know the probability of not A and B. So I've just converted that into set notation. Not A is A complement and is intersection B. So we can use our properties here on the left to solve this, but I'm going to maybe do this in a more simple and intuitive way just by drawing a picture and using our Venn diagrams. The written solutions, which are also on Moodle, have a more like computational and complicated way of solving this one, but I'm going to show you a more intuitive solution for this. So we want the probability of not A and intersection B. So I'm going to draw my two events, A and B, and I'm going to shade in the diagram corresponding to what I want. So I'm going to shade in not A, intersection B. So not A is everything outside of the circle A. So it would be everything here, right? Everything outside of A. But I want this intersection B. So I want what's not in A and in B. And that is just this area here, right? It's in B and it's not in A. Well, this shaded area is B minus the intersection, minus this intersection of A and B, this little area in the middle. So by drawing my picture, I can see that the probability of not A and B is equal to the probability of B minus this shaded area here, which is the intersection of A and B, that overlap area. Well, I know what the probability of B is. It gives me that here. That's 0.4. But I don't know what the probability of the intersection is. I just know the probability of A, B, and their union. Well, if I want to use those three things to find probability of the intersection, well, notice that I have this handy property here. And that says that the probability of the union is equal to the probability of A plus probability of B minus the probability of intersection. Well, I know 3 out of the 4 of those things. So I can plug in this, this, and this, and just use some simple algebra to find the probability of the intersection. So let me write down this property right here. And that says probability of the union is equal to the probability of A plus the probability of B minus the probability of their intersection. They told us that the probability of the union was 0.6, so I'm just going to plug that in. The probability of A we're given was 0.3. The probability of B we were given is 0.4. And I want to solve for this unknown quantity. So I'll just do some simplifying. I can rearrange, move this to the other side, and move 0.6 over to this side. So I can add probability of A intersection B to both sides. It'll cancel out on the right. So it's 0.7 minus 0.6. So the probability of the intersection is 0.1. So now I can go back here and solve for this probability, which I wanted. Probability of the intersection we found was 0.1. So the probability of not A and B is 0.3. Awesome. We'll use a similar approach for the last part, which is the probability of not A or not B. And I'll just rewrite this in terms of set notation. So complement of A, union, complement of B. Because it says the word or, I know we're using a union. Let's see if we can draw a picture to help us visualize which probability we want. So I'll draw my box, my A and B. And I want to shade in not A or not B. The union of two events, I simply smush those two events together. Not A is everything outside of A. So that's everything not in the A circle. Shade all that in. Not B is everything not in the B circle. So that's everything outside of B. Shade off that in. So I want to find the probability of all this shaded area, right? That's not A, union, not B. Well, everything is shaded in except this little area in the middle. So the probability of the shaded area is everything minus that part in the middle. Everything, well, that's 1 minus this area in the middle. Well, that area in the middle is precisely the overlap between A and B, or the intersection of A and B. And in the previous question, we found that that was 0.1 using some of our handy properties. So the probability of not A or B is all this shaded area, and that's 1 minus the unshaded area. 1 minus probability of the intersection. So that's equal to 1 minus 0.1, which is 0.9. And that's it.